So curl is about the rotation. So rotation what? Rotating what? It's a rotating around the point by the vector field, and it's the work done per area. And if it's not 0, then it's rotating counterclockwise. If it's 0, it means that it's not rotating around that point. And what if you have a negative rotation? Let's say we have y minus x. Rotation is minus 2. So whenever we have a circle, we kind of thinking about this direction of this movement around a circle or closed curve as a counterclockwise direction. So it's always moving counterclockwise. So whenever you have a positive value, then it means that you're moving in the counterclockwise or doing work in counterclockwise direction. So it's if it's negative, then you are moving in the clockwise direction. Okay, so it means that every arrow is opposite direction. So the circle, this fan is rotating clockwise direction. So it's only differ by the rotating directions. Okay. All right. So any questions about this? I mean, there are many. So frankly, calculus, most calculus book introduced this green theorem in order to say, oh, this complicated line integral can be made into a simple double integration using green theorem. And I don't think that's the essence of this green theorem. The green theorem is not made for this purpose. Okay, so there in calculus, most calculus books are kind of using this as to make questions more complicated, but I don't like it. So I mean, I could give you the example like that, but I don't want to give an impression that this green theorem is just for the computation reason. So any questions about the meaning of the green theorem here? Yes?
I would ask about the curve.
Curve, yes.
About the rotation around the point or area, regardless of the shape of the unit area.
Yeah, regardless of the shape.
So we can assume there is shape, rectangular, or sphere or something.
Yeah, it can be sphere or rectangle, but the important thing is per area means that if you fix a shape, then you only get approximate value, not the exact value. So if your point is here and you want to compute the rotation or curl at this point, but you want to, you can get the exact number by plugging the qx minus py at this point in this formula. But if you want to compare the value with this meaning, then you inevitably have to fix your domain and the shape of a curve, closed curve. Then what you get by this meaning is the approximate value, approximation of this value. So if you get a smaller and smaller region, then you get closer and closer to the real value, but you're not gonna get exact value here. So basically, we are talking about approximately work, but what I mean by per area is I'm not thinking about actually 1 unit area. It could be a 0.0000 unit area, but still I'm trying to get the ratio, how much the work has to be done on this area. So this ratio will be always approximately equal to this. So let me state more clearly here. So we have, if I write it more clearly, and this is rotation is integration p dx plus q dy over c epsilon. So if you take the ratio, it's approximation, but if you take the radius goes to 0, then it's going to be the exact rotation, because that's because of the green theorem here. So integration is an approximation if you take the sum, but after taking the limit, then it's exactly the same. So taking the limit means that we're taking the integration, the real integration. But by taking the ratio, we're kind of doing it by summation. So here, the integration, the line integration done on the circular boundary of radius epsilon at that point. And this is the area of a circle. Okay. So this is more rigorous way of writing the definition by limit. But this one is actually just the meaning. Any other questions? So I want to give a slight variation of the Green theorem. Think about this one. So let's see. Minus q dx plus p dy. Okay, here I'm integrating p comma q, right? But here I'm integrating minus q comma p. So I can still apply Green theorem as if q were p and p were minus q. And then what happens is whatever here is, whatever that multiplied to dy will be taken partial derivative by x. So it's going to be px here, right? So whatever multiplied to dx will be taken partial derivative of y, so in minus, so you have a minus already, so they're going to be plus and qy, right? And then integrate over d. So I want to think about this meaning here. So let's see, here's my xy plane, okay? And here's my curve, or not, it's not entire curve, it's just partial, partial. So here is my point. So we have xt and yt, okay? And then let me think this way. So we have so we have this vector field at this point whose coordinate is p comma q. So when we take a normal integration, like in this Green theorem, what we are doing here, but let's think about another notation of line integration. So we can write the line integration as the following, ds, and this can be also written as f c prime t dt. So here now t has to be the integration has to be for t, so let's say a to b. So here what we are doing is we are looking at the velocity, the instant velocity of the point on the curve, so that we're taking the inner product, which means that we are looking at the shade projection of the vector field onto that velocity direction. Okay, so here, let's say this is the movement c prime t, and we are taking the projection of pq on this direction. So we are actually integrating this amount of vector times the dt, or distance, so that we get the entire work done by summing up all the small works done that along this small segment of line. But however, let's look at this one. What does it look like? Well, we're not actually looking at this direction. So here, let me rewrite this. Minus q x prime t dt. So dx is dx over dt times dt. So dx over dt is x prime. So I can rewrite this way. So and then what? P y prime t dt, right? So and then let's go backward here. So we have PQ, we had PQ, but in order to have this integrand, I need to multiply P with y prime, right? So I need y prime over here, and I need to multiply Q with minus x prime, so minus x prime here. So this is my original vector field, and here, this is not the c prime because it's not x prime comma y prime. Instead, it's y prime minus x prime. So we had x prime, y prime on the tangent direction. What is y prime comma x prime? So y prime minus x prime is actually this, y prime minus x prime. The perpendicular direction to the tangent direction of the movement along the curve. So it's a tangent perpendicular to the curve. So we are taking inner product between the vector field and the perpendicular direction to the curve. So we are looking at this projection, not this projection, right? And then what we are doing here is we're taking the projected vector and then multiply with small distance, small line segment here, and then sum them up. So what we are doing, and then that's the left-hand side that we are talking about. And on the inside, we're talking about integrating this thing, px plus qy. So we can understand this identity, well, actually coming from the Green theorem in a different perspective. So on the left-hand side, I'm looking at some kind of flux. How much the water or liquid is coming out along the boundary of a circle or a curve here. So at each boundary, it's a line segment. So I'm multiplying the length of line segment with the velocity. The velocity means that it's amount of water or liquid or air that flowing out across the boundary. And then the unit will be the amount times the length. So amount means the velocity, sorry. So first of all, the unit is the velocity times the length. The velocity being the unit of p comma q here, and the length being the unit of this part, c prime t part. And then this velocity can be computed as the length per second or minutes or whatever, the time. So let's say time. And then times length. So therefore, length times length is the area, or it could be amount per time. So on the left-hand side, what we actually compute is not the work. In this perspective, we are computing how much the area or amount of whatever is flowing out across the boundary per time, per unit of time. So it's called a flux. Also flux. I mean, it's the definition of word flux. It's the amount of thing coming through a certain boundary per time. So don't forget about the time, not exactly absolute amount of liquid. It's how much it is flowing out per time. So that's the left-hand side. And what's the right-hand side? It says that you can compute the flux over entire boundary of this closed curve by simply integrating this thing, the value, over the domain bounded by C. And this is called divergence. So here, definition. So divergence written by div here is px plus qy. Okay, so let's summarize. So this identity comes from the Green theorem. It says that the flux across the closed curve equals to the double integration of divergence. Okay, so what does that mean? Okay, so I just read the definition. The divergence, let's think about the meaning of divergence. So it's so if I have small d or small c, like taking a small radius, then this double integration is almost equal to area times the divergence, right? So the divergence can be almost equal to area and integration. So basically, it's the flux over the area. So what does that mean? Flux is something flowing out across the boundary, right? So you can imagine there is some kind of fountain. Let's say this is 1. What does that mean? So divergence equals to 1. What does that mean? It means that you're looking at a point where you compute the divergence, and then if you take the small circle around that point, then there is something coming out from the source, this point, across this boundary with a speed of 1, so with the rate of 1 unit of area per time, right? So that should mean that there is something that like a fountain that springs the water or liquid in that source, and then it's always flowing out from that source. So that's called divergence. Something is expanding at this point. So divergence 0 means that nothing is actually springing out, right? So for example, let's look at the divergence of these two particular vector fields. So if f is xy, the divergence is 2, right? And if f is minus yx, then divergence is 0. So what's the difference between these two vector fields? So this one, as we have already seen before, so it's running away from the origin, right? So and as it moves away from the origin, the arrow gets larger. So if you put the small disk around the origin, then you can always say that, oh, something is coming out at this origin, right? So therefore you can detect whatever that is crossing the border of the circular boundary. But also it says that it's always constant no matter where you point, where you compute the divergence. So even if you put the points away from the origin, if you put the small disk, then look at this. There are two sides. So in this side, it's flowing in, right? But in this side, it's flowing out. But there is a difference between the points from where the thing is flowing in and where the thing is flowing out. When it's flowing out, that is actually farther than the place where it's flowing in. So it's getting, something is flowing out more than something is flowing out on the other side. So it's always something, looks like something is going on in between at this point. It actually has this meaning. This 2 means that at this point, you can imagine that something is actually sprung out, that more is coming out along this boundary. So even if it's kind of canceled, that it's something flowing in this side, there's more that's flowing out, so that it makes actually more is coming out from this disk. And how about this one? Look at this vector field here. So it was something like rotating here, right? So it says the divergence is 0. What does that mean? So if you put a small disk on the origin here, nothing is going out or in, right? Why? Because the vector is moving along the circular boundary, right? So it's running through the rim of this disk. So you can't detect anything going up, out, or in. But it's the same situation as you put the disk on the other side, on the other place. So let's say something is going in this direction. There's some part of the rim of the circular boundary that comes in, and there's other part that goes out. Divergence 0 means that whatever that comes in, the total amount that goes into the disk is same as the amount that goes out. Same amount goes in, same amount goes out. Therefore, nothing seems to be emerged from the inside of the disk. So that's the meaning of a divergence. The word divergence actually means diverging, right? It's actually expanding, going all directions. So that's the actually good name for meaning what this is. So basically these two concepts, divergence and rotation, based on this Green theorem. Okay, so you see the logical flow here. So people might thought about this divergence and rotation first, but whenever you try to explain the meaning, you should go for the Green theorem first, and then from there you can infer the meaning. Okay, so any questions?
What is the unit of divergence?
Divergence, unit of divergence?
Yeah, we say like flux is kind of area divided time.
Yep.
So what's about divergence?
Divergence,
1 divided by time?
yeah, it looks kind of that way. Well, let's say it depends. So let's say your amount could be, well, it's the same. So yeah, it's kind of tricky to say the unit of divergence is 1 over time. So what does that mean? So physically, yeah, physically I don't know. Physically I don't know what it means to have a unit 1 over time.
How can I understand like amount of
But I would rather just stick with this unit. If I have to give a unit, then let's say meters square per second per meter square. Because that kind of, I mean, you can cancel this out, but if you just eliminate all the units that is involved in the formula, then you lost the meaning, well, for example, what's the unit of Planck constant? Well, we can have a unit, but the unit itself doesn't give any meaning to the Planck constant, what that is, right? So, I mean, I'm not saying that the canceling is useless, but it's just saying, for right now, I mean, if it's not a constant, then we don't have to always canceling out the units so that it make always to make it the most neat form. So you just put it. Just think. I'm comfortable with this, but I'm not comfortable with 1 over s and trying to explain the meaning.
so how we can like think about the meaning of divergence. If the flux is amount of substance is going from the
Boundary.
Yes. Of the region.
Yes.
For a specific period of time, it's like flux.
No,
Can
per
you
time.
explain?
Per time. Yes.
So then divergence.
Then divergence is flux per area. Yeah, amount of flux per area. Yes.
So what is the meaning of divergence? Flux per area?
I mean, it depends on what flux is. So if you think about the electric field, let's say the water can be measured by a unit of length or unit of area. But let's say you're talking about flux of electric fields or magnetic fields. Well, what is the meaning of the flux? Well, maybe it can be computed or measured by some physical tools, but there is a unit, not the unit of length or area, right? The flux has a unit, but the divergence measures not just the flux, but it's flux per unit. So, flux per area, flux per area. Okay. So if the area is big, let's say you're taking a big region around that point, then you're gonna get less accurate value of your divergence, but still the value that you get as a divergence will approximate the amount of flux that is crossing across the border of all the boundary that surrounds the area, divided by the area. Okay? So it's kind of a ratio. So it's not, so if you just think about the flux, if your area is larger, then your flux gets larger. It could get larger, right? So divergence is something independent to the shape or area of the region because it measures the ratio between two. Okay? So actually it depends on at one point. At one point I want to see what's happening. So that's why I'm making it smaller and smaller until I get this. So maybe I can just mimic this definition of rotation using the limit. So let's say rotate a divergence of f is limit where I can minimize the make it radius smaller and smaller and then integrate over c epsilon minus q dx plus p dy or flux. Okay. All right, there's actually getting interesting. If you understood this, then we can make it into three-dimensional. Everything becomes three-dimensional. So let me define this first. There are notation. So here, definition. I'm sure that you've probably seen this in physics class. So nabla, I already introduced this when I introduced the gradient. So nabla is an operator. It could be operator acting on two-dimensional vector field, or it could be acting on the three-dimensional vector field. So in that case, we take nabla to be the operator. Looks like a vector, but coordinate, but its entries are operator, not a number. So it's just a symbolic notation here. So here first, when I have, let's see, so when I have a vector valued, when I have a real valued function p, then f, then the nabla f is just applying these two operator on f as if I taking a distribution rule. So the f is applied here, f is applied here, so it becomes a two-dimensional vectors. So if this is two-dimensional, and if f is three-dimensional, that has three variable, then I'm assuming I'm defining this nabla f to be three-dimensional vector or vector field given by these coordinates. So nabla itself is not a vector. I mean, it's not a vector because vector always has to have some value, but this does not have any value. It's now vector when you apply nabla to a function. Okay, so there are two different kinds. So it depends on the context. If I'm talking about two variable function, it's two-dimensional, and three-dimensional if it is three variable. That's one thing. And then there's another. So let's say I take vector field f arrow in this case, and then take a nabla, and then take an inner product. The notation is different. So sometimes some textbook omit this inner product symbol because it's obvious that if you have a vector field, you cannot simply multiply two vectors. Whenever you have two vectors multiplied, it has to be considered as the inner product between them. But I want to put it in the inner product here explicitly. So then what happens? So let's say my f is two-dimensional vector field, PQ. So then I'm taking an inner product formula. So as if this operator is multiplied to P, but it's not really multiplication. Operator is acting on P. So this P is acted by the operator DDT, and then plus the second multiplication, dq dy. So this is what? Divergence. Okay, so this is actually, sometimes people say this is Steve vector field. Actually, we did here. But another case, if you have three dimension P, Q, R, then you go for the three-dimensional nabla operator. So there P, there X, there Q, there Y, and there R, there Z. Okay. And there's one more definition. This. Nabla cross product F. So how do you define cross product? Well, how do you compute this? So first of all, you take 3 by 3 matrix with the first row ijk, meaning that 1, 0, 0, 0, 1, 0, 0, 0, 1, and put the first vector on the second row here. We have, so in this case, we always assume that F is three-dimensional. Okay, F must be three-dimensional. P, Q, R. There X, there Y, there Z. Okay, and next put the coordinate of P. F, which is PQR, and take the determinant of the 3 by 3 matrix. So it's RY minus QZ and PZ minus RX and QX minus PY. Okay, so by definition, this is called curl of F, and it consists of these three coordinate functions. But don't try to remember this because you're always confused. So just go for this definition of cross product. Just take a nabla operator and then vector field F, and then do the matrix determinant formula here. And okay, so these three are everything that we need to understand or remember before we proceed. So, by the way, look at this last coordinates of the curl. So this curl PQ, QX minus PY, it's the curl of two-dimensional vector. So how come we got this? So it's not a coincidence. So if you have a two-dimensional vector, a vector field, then you can kind of thinking of this as F, vector field F, being two-dimensional, but it has 0 on the third coordinate, then what happens is I, J, K, del X, del Y, del Z here, but P, Q, 0, right? So 0 here, 0, 0. And yeah, so here R is 0, so we kind of minus QZ, PZ, and QX minus PY. So basically, here we just take the third coordinate, and then this could be just rotation field here. Okay. It's not a coincidence. So let me state two important theorem, like a green theorem. So first of all, Stokes theorem, and second, divergence theorem. So divergence is not a person's name. Stokes is a person's name. So Stokes theorem says if I have a curve which is closed curve, and if I take P dx, Q dy, R dz, so basically means if you have this dz part, that means your vector field is three-dimensional vector field, and C, the curve is in the three-dimensional space. Okay, so Stokes theorem states that in that case, this is equal, not this one. So double integral of this curl ds, the surface integral of a vector field, where the vector field is not the original vector field f, it's the curl of vector field. Look at this curl, the definition of curl. It's already three-dimensional vector field. So by taking a curl, you get, you transform your vector field into another vector field. So that's the Stokes theorem. So there's something more that I need to explain, but that's just the essence. And let's also think about the divergence. And the divergence theorem says that if you have the surface integral over the closed surface, so closed is represented by the circle around this double integration, is same as triple integration over the volume of divergence of this vector field. So there are many variations to write this Stokes theorem. For example, if you don't want to write this dx, dy, dz part, then you can just write it as a f ds if you want to. And well, you can also rewrite this in different notation and also write this in different notation. But let's maybe today can think about the meaning of the Stokes theorems and divergence theorem. So first of all, Stokes theorem, what does it say? It says two things are equal. What are they? One thing is the line integration of three-dimensional vector field. There are two important keywords, line integration, and it's about three-dimensional vector field. Okay? And also there's another thing that you have to remember. It's the closed curve. It's not any curve, it's a closed curve. It's a line integration along the closed curve. And on the other side, we have a surface integral of vector field, not the double integral. It's a surface integration of vector field. And now, when you take a surface integration of vector field, remember that you need an orientation, right? We talked about this yesterday, on Monday. There are always two orientations on a surface. I mean, if there is a orientation, there is always two. And we need to decide which orientation we are taking the surface integral. So, and also here, there is an orientation of line integration. So here is the way you can take the orientation. So, and what's the relation between C and S? So S is the surface and C is the boundary of that surface. Okay? So there are not many conditions. You just write down every condition that you can think of, then you will see that it's clear. So here, if you're walking, so let's talk about the orientation. So if you're walking along the curve, which is the boundary of a surface, And let's say you put your heads up to the orientation direction. Let's say you're walking on this direction. Then your left-hand side must be on the surface. Your surface must be on your left side. So it's either way. So if you take an orientation of a surface, let's say this is my orientation, which gives me the perpendicular direction to the surface at every point, then this will be your where your heads are up. Your heads up to the orientation of a surface. And your orientation of this curve boundary is the direction where your left-hand side must be on the surface, must be the surface. So the orientation of surface gives the orientation of curve, and vice versa. If you have an orientation of curve, then if you're walking along this curve, then while your left-hand side, the surface is on your left-hand side, then the direction where your heads are up is the orientation of surface. Just remember this figure, or you can remember by right-hand rule. If you just rotate along the circle or along the boundary with your forefinger, then the orientation of surface must be the direction where your thumb is pointing to. Okay, so that's everything that we need to explain these equations, Stokes theorems, on the left-hand side and right-hand side. Anything else we need here? So I don't think so. We explained everything. So everything is clear. How about the divergence theorem? Look at the divergence theorem. It's the same thing. So we have two things that are equal. One is the surface integration. The other is the triple integration over the volume. So first of all, let's look at the surface integration. It's still the integration of vector field. So we need the orientation. So, and also, this surface is closed surface. Okay, I know what the closed curve is because it's a curve whose starting point is same as the ending point. What do you mean by closed surface? So whenever you have a closed, means that it has no boundary. So closed curve means that it has no boundary. What's the boundary of a curve? It's the point. There could be two endpoints, right? If you don't have any two endpoints, then it's closed curve. So closed surface means that it has no boundary of a surface. What kind of surface has no boundary? Sphere has no boundary, right? There's a song about this round sphere in Korean song, right? So it has no boundary. If you go walk and walk, you're not gonna reach to the end, right? And then the orientation, okay, so we can fix one orientation, either outward or inward, it doesn't matter, okay? So, and then right-hand side, now let's look at this one. So it says that we have a divergence, which is the real valued function. It's not a vector field anymore, so it's just a three-variable function. We're integrating over v. So now what is v? Well, it should be v. So v is the region surrounded by the surface S. Now, what is surface? The surface here, and what do you think the V should be? So let's say if the surface is the sphere, is V inside or outside? We don't know until we have orientation. So the V is the region inside according to the orientation, where orientation pointing the outside. So if the orientation is the outward of the sphere, then the volume is the inside of the sphere. But if the orientation is pointing inward, then the volume is outside of the sphere. So V is not determined by the surface itself. It's determined by surface, which gives the shape, and orientation. So it's the inside of the surface according to the orientation, where orientation is the outside. So then everything is clear. So we're just taking a triple integration of three variable function. And the divergence theorem says that these two are the same. Okay? Now, I'm just explaining the equations. What's the meaning of the Stokes theorem? What do you think the meaning is? So here, what we are doing here is the work along the curve, closed curve. Here, we are taking curl, kind of vector field, taking curl and integrating that curl on the surface. And it says they are the same. Let's look at this way. So you have to go for the meaning of the curl. So it's actually, it's similar to chicken and egg. So which one is first? You have the meaning of the curl, then you can get the meaning of the Stokes theorem. If you get the meaning of the Stokes theorem, you can get the meaning of the curl, vice versa. So either way is fine. But you need to start from one thing. So let's start from this Stokes theorems and then try to get the meaning of this curl. So let's say I have a point, okay, and I have, let's say, plane in certain direction. And let's say this is my, so this, you can consider this as your surface. And this is your orientation of your surface. And let's take a small, very small circle centered at that point on that sphere, on that surface, which is flat. Okay? So if I decrease my epsilon, the radius, small and small, on the left-hand side, I'm keep taking the integration along the boundary, which gives me the amount of work to rotate a point around that center, right? That's the work done by force vector field to rotate. And on the right-hand side, what I have is, since my disk is very small, this vector field will be almost constant vector field because the value of the x, y, z coordinate of these three coordinates will be always almost equal at every point in this small disk. So I can say this is mostly constant. So what happens is when I have a constant vector field here, let's rewrite this. So it's S times whatever this is, constant, times the orientation times, so here the multiple is the inner product here, and ds. So surface integration of vector field can be written as the surface integration of a real valued function like this. So what we have here is the inner product between the curl and the orientation. So whatever the curl is, let's say this is my vector of curl, okay? I'm taking inner product, so I'm projecting it down onto the direction of n. So let's say this is my projection. So I'm looking at this amount, this much, just length of this much, okay? And then integrating over s. But I said that this is always the same, constant on every part of the disk because disk is very small. So I can just say this whole thing is just constant. So now blah f, and as a constant comes out, and then ds, right? So then, what is this? So this is times area of s, okay? So I want to think about what the meaning of this. So it says that if I have the rotation or curl, and if I take a certain orientation or a certain velocity of certain vector which is the perpendicular direction of the surface, then I can move the surface area over here on the left-hand side. It has to be equal to 1 over area of the line integration of the vector field, right? So now we can think about the meaning of the curl. And I think not many textbook gives the concrete meaning of the curl in this sense. So I want to try this. So let's say I put my surface, which is parallel to xy plane. And my orientation is positive z-axis. Okay? So and then what I get here is the last coordinate of my curl, qx minus py. Because in that case, the n orientation is 0, 0, 1. When you take the inner product between 0, 0, 1, you always get the last coordinate, right? So in that case, the value, the last coordinate value, means that it is the work done to rotate around that point per area, which is exactly the same meaning as the curl of two-dimensional vector field. How about when n is 0, 1, 0? So let's say you put your surface parallel to xz plane, and then you set your orientation of that vertical plane to be the positive y-axis, then this gives you the y-coordinate of your curl, this one, and it means that if you want to rotate a point around that point on the plane, which is vertically standing in this 3 dimension, then the amount of work that is required per area is the y coordinate right here, this amount. And you can do the same thing with the surface, which is on the ZY plane, and your orientation is positive x plane, positive x axis, and then you can give a meaning for the x coordinate here. Okay, I just gave you the meaning of each coordinate, and what does that mean? So I want to think of this way. So as I said, rotation or curl of two-dimensional vector field gives you how much the vector field is going to rotate a fan, rotate the blade of a fan if you put your fan on that at that point, right? So let's think about the situation that your vector field is representing a flow of air. So here, right here, there is an air, and they're always moving in some direction. Let's say go outside, and then imagine you go outside, and there is lots of wind, and the wind is blowing here and there. And then at the moment, let's say assume that we kind of measured which direction and how much the wind is flowing in one specific position here. And then let's say that's your vector field. Okay, so vector field gives you the amount of wind is blowing in certain direction at every point. And what's the curl of that vector field means? It means that if you put your fan, if you put your paper fan, whatever, in certain direction, then it will rotate because of the wind, right? And you want to know how much the fan, how fast the fan will rotate at certain direction. So the amount of the speed of rotation of fan on certain direction is measured by this curl. Because if you take the inner product with the curl and the orientation of your fan, this amount will give you the proportional rate of how much fast does the blade of your fan is rotating. So let's say I want to have this thing here. So let's say this is your fan. This is the surface of your fan. So fan is probably rotating in this direction, whatever. So here's the wind, and then I put up here. So it's pointing that direction, right? So if I take this fan here and then see how fast the fan is moving, then this speed of blade will proportion to the last coordinate of this curl. Okay? And then I set the xy axis arbitrarily here. And then let's say I put my fan straight up here, parallel to yz plane. And then like this. And then I'm going to see that the blade is rotating in certain speed. Not in the same speed as before, right? Because it's different wind is blowing perpendicularly in this way. So the speed of blade rotating around the fan will be proportional to the x-coordinate of the curl, and so on. So if you have an arbitrary position here, let's say in this direction, how much the fan will rotate? Okay, so you have to first calculate the perpendicular direction of this face of the fan, and then take that as your orientation. And then since you know the vector field, take the curl, and then take the inner product. Whatever that comes out as a number will be proportional to the rotation speed of the fan. So that's the meaning. It's the curl. How it curl that determines the speed of the rotation of your fan. You can apply that to the liquid situation. Let's say the current water is flowing in the three-dimensional bottle, and then you want to, like, say, measure how much the turbine is moving. Let's say you're doing in a you're generating electricity using the water turbine. Then you want to see we want to kind of maximize the speed of rotation, right? So then you want to know in which direction you want to put your turbine to point, and pointing to which direction to make the maximum speed of rotation. So then you go for the curl. So you just calculate the curl if you can, and then take that as your direction to maximize this value, because the only way you can maximize this is to get the orientation equal to the direction of this. All right, so basically that's the meaning of the Stokes theorem. That's the meaning of the Stokes theorem. So basically, I use the Stokes theorem to get the meaning of the rotation. Let's go backward. Let's say we know the definition of the meaning of the rotation, meaning of the curl, and then what the Stokes theorem says. So here's the situation. Here's the surface, big surface, and here's the let's say. By the way, so here is the boundary, okay? So going here and here and, okay? So Stokes theorem says, if I take up all the curl in the direction of the orientation, so just calculating how much work is required to rotate every point around that point, and then the Stokes theorem says that it can be calculated just by taking the integration along the outermost boundary of the surface. It doesn't have to go inside. It doesn't matter what's going inside. It always depends on what's going out on the outside or the outmost boundary here. So think about this case that maybe I can divided out the surface into smaller regions. So what happens is, on the right-hand side of the Stokes theorems, I'm taking a small area, which is ds, with the orientation n, okay? And then at this point, I have a curl, okay? So I'm taking the projection of the curl onto the orientation direction, and then multiplying this length of the vector, with the area of a small region, and then sum them up, okay? So basically what I'm doing here, because the curl is measuring how much work has to be done in order to rotate the point around the point per area, since we multiplied the area unit, this actually gives you how much work has to be done to rotate around this small area, boundary of this small area. Again, so if I take, where's my new one? So here's this, my new one. So if I take curl and then inner product with the orientation and multiply with ds. So basically, all I need to do from here is just sum them up or integrate. Okay, so before I do that, this amount means that it's the work done to rotate a point around the boundary of this small region. Not per area, because I already multiplied the area. It's exactly the work. So this is the work to rotate around the small area. So I'm doing this for every point. So I'm not doing the same point at the same point. I'm doing it at the next point. So I'm taking a small part, next part, and the next part here. So on this next part, what I'm doing is the same rotation, same rotating direction, because I have the same orientation. Like it's not exactly same vector, but the direction is all same. So in that case, what I have is I have these paths of work and these paths of work. If I combine them, on this part, I'm going upward, kind of upward, going up. And on this patch, I'm going downward. So I'm doing work to up and down on the same line. So it cancels out. So if I add the amount of work together, then it actually is the work done to rotate around the bigger region combined here, right? So I can do this for every other point, and what happens? If I get it larger and larger, what left is just this boundary work, okay? So it's like you have, what do I say? Do you call it crank? Or what is it called? So I've just forgot the name. Or is it called if you have this? What is this thing called? Sorry. Gear? Yeah, gear. Yes, let's say gear. So you have, so inside, let's say we have lots of gears, small gears. Okay. So we want to rotate the gears. So we can rotate the gears for a small amount Okay, so how do you rotate the gears? You can rotate each gears, and then you have to do a small amount of work for each gears to rotate everything. But it says that you can rotate the entire gear by rotating the outside because it's all connected. Right? If you rotate one, then the other is rotating as well. So it's not really physically possible to implement here, but just imagine that this kind of situation. The one rotation affecting another, and then let's say if you want to do a rotation on every gear inside the sphere, then basically what happens is you can see the moving gear on the outside, not in inside, right? So what happens, so it's same as rotating the outside gears will automatically rotate the inside here. So that's another way you can explain the Stokes theorem. I'm not saying this is the only way. I'm just saying that I just thought about this for a long time and want to share this. And okay, so let me briefly mention about the divergence theorem and call it here. And the divergence theorem, what we're doing here is on the left-hand side, we have a vector field, and we're taking over the surface. We're actually finding the flux. We're computing the flux. We're computing the flux across the surface, but how do you measure how much water or liquid is coming out across the boundary over the time? You can see how much it sprungs inside. If there's a fountain, you can just measure how much water is flowing into this region, and then that will be just same as amount of work that you checked how much is flowing out from across the surface, because water is not compressible, right? If you're just pouring the water 2 liters per second, then you don't have to measure how much water is flowing out in this pipe. It will flow out in 2 meters per second, right? So on the right-hand side, it measures how much is diverging, how much is coming, it's generating inside of the sphere, inside of this region. So at every point. So basically, we have seen 2 versions of Green theorem. The first Green theorem, it just measures how much, what the meaning of the rotation is. And the second version is about what the flux is, right? So you can see the analog here. So the Stokes theorem is kind of analog to the original Green theorem about the rotation. And divergence theorem is analog to the Green theorem, another version of the Green theorem, which measures the flux, right? So because it's a flux, so in the Green theorem, we had a flux across the one-dimensional boundary, which because it was the two-dimensional region, which has one-dimensional boundary. But here, our flux is across the surface, which is two-dimensional in three-dimensional space, and this surface is also closed. So you're not looking at the open end here. It's always bounded in full boundary here. And then you want to see how much is flowing out in this across this closed surface. All you need to do is how much is flowing in the inside of the region according to our orientation of the surface. So let me think about this way. So inside, outside is very important concept. So so here we have hollow sphere here. So in the divergence theorem, the surface S doesn't have to be just one connected surface. It can be a collection or union of surface that bounds some area. So let's say I'm looking at the area in between these two spheres. Okay, this is my V. Okay, then my surface S is union of two spheres, S1 and S2. S1 and S2. So here, what I'm looking at, I also need to talk about the orientation. So since I want to put my V as an inside of this sphere or surface, so orientation on S1 must be this direction, and orientation on S2 must be this direction, because that gives you V on inside. Okay, that makes V inside of the sphere, of this region. So you cannot say S2 has the same orientation in this sense, I mean, it has the same orientation, but it cannot be this direction, because then V is not inside according to the orientation of S2. So when you apply the divergence theorem, if it's not if the volume or the surface is not simple, then you have to be careful about choosing the orientation.